Hello, hi, I am Gangadhar, lecturer in mathematics from Giraj Government College, Nizamabad. So now the topic basic third year mathematics, paper 5. So in vector space, one of the chapter, basis of a vector space. So now the definition of the basis. So basis definition is first B is non-empty set and B is linear independent and V equal to span B, then we say that B is basis for the vector space. A set of vectors in a vector space V is called a basis if the vectors are linear independent and every vector in the vector space is a linear combination of the set. So that is B is non-empty set first and B is linear independent and V equal to span of B, then we say that B is called basis for the vector space. So basis means it satisfies two conditions, B is linear independent and span of B equal to V. So then we say that B is basis for the vector space. The standard basis of R to the power n is so E1, E2, so on En. Standard basis for R to the power n is B equal to E1, E2, so on En. So E1 equal to 1, 0, 0, so on 0, E2 equal to 0, 1, so on 0, En equal to 0, 0, 1. Suppose it is the standard basis of R to the power n. Suppose we want a standard basis for R to the power 4. Means it contains 4 vectors E1, E2, E3, E4. E1 equal to 1, 0, 0, 0, E2 equal to 0, 1, 0, 0, E3 equal to 0, 0, 1, 0, E4 equal to 0, 0, 0, 1. So it is standard basis of R to the power 4. Suppose we want R3. R3 basis means it is similar to we will take 3 by 3 unit matrix model. So same way we standard basis define for polynomial vector space. So polynomial vector space is Pn of x and in the polynomial vector space Pn of x elements are 1 x, x square, so on x to the power n. Pn means it is a set of all nth degree polynomial set. It is form a vector space with respective addition and vector addition and scalar multiplication. So here standard basis of Pn of x is 1 comma x comma x square, so on x to the power n. So suppose n plus we will take 3. Standard basis of P3 of x is 1 comma x square comma x cube. So this way we define standard basis of vector spaces. So one note is there. So in a matrix A, pivot columns are linear independent, they form basis. So in matrix A, pivot columns are linear independent and they form basis. So second note is let A be an invertible n by n matrix, say A equal to A1, A2, so on An, then the column of A form a basis for R to the power n. So in matrix A, columns form basis for R to the power n. So in invertible matrix means pivot columns form. So in matrix A, pivot columns form basis of vector space or matrix for A. So by the inversible, so let A be invertible n by n matrix, say A equal to A1, A2, so on An. Then the column of A form a basis for R to the power n because they are linear independent and they span R to the power n by invertible matrix theorem. So total number of non-zero rows in matrix is called rank of matrix. Total number of non-zero rows in matrix is called rank of matrix. So let A equal to V1, V2, so on Vn be n by n order matrix and rank A equal to n. Then the vectors V1, V2, so on Vn are linear independent and they form basis for R to the power n. So in the matrix A equal to V1, V2, so on Vn, n by n order matrix, its rank is A equal to n. So the matrix has n rows and rank is n. Then those vectors form linear independent, and those vectors form basis for the r to the power n. So now example. So the vectors E1, E2, so on En are, we know that these are linear independent vectors, and they form basis for r to the power n. So next problem, V equal to P3 and the set S equal to 1 comma t comma t square comma t cube. Show that S is basis for V. Show that S is basis for V. So what is the basis definition? So first, S is non-empty subset of the vector space. First condition, S is linear independent set and V equal to span of B. Then we say that B is basis for the vector space. So here first we show that given vectors are linear independent. So linear independent means we write linear combination of the vectors, and that linear combination we equate to 0 bar. So in that 0 bar, in the linear combination, if all scalar values are zeros, so in the linear combination using all scalar values are zeros, then we say that given vectors are linear independent. So here we write first linear combination of the vectors c1 into 1 plus c2 into t plus c3 into t square plus c4 into t cube equal to 0 bar. So if a polynomial is 0, then it is certify all right side values 0. So here we equate 0. So right side 0 bar. 0 bar is a 0 polynomial. Here given vector space is polynomial vector space. In the polynomial vector space, 0 vector is the 0 polynomial. So 0 polynomial means that value we write 0 plus 0t plus 0t square plus 0t cube. So compare both side coefficients. First constant values c1 equals 0, t coefficients c1 equals 0. First constant value c0 equals 0, t coefficients c1 equals 0, t square coefficients c2 equals 0, t cube coefficients c4 equal to 0. So here c1, c2, c3, c4 constant is c1 0, t coefficient c2 0, t square coefficient c3 0, t cube coefficient c4 0. In the linear combination, all scalar values are zeros. So therefore we say that S is linear independent. S is linear independent. So next we write V equal to span of B. So V equal to span of B means, so elements of V, it is a third degree polynomial. Span of B or span of S. Span of S means, so here span of S means, so linear combination of the vectors. So A into T plus B into T plus C into T square plus D into T cube. So suppose, so the vector we need to find constant c1, c2, c3, c4 such that c1 into so on, right? Both sides we compare the values, we get c1 equal to a. So in the P3 third degree polynomial of the form a plus bt plus ct square plus dt cube, and elements of S we write linear combination c1t plus c2t plus c3t square plus c4t square. So we equate these two polynomials. If we get constant values c1, c2, c3, c4 values, so then we say that polynomials vectors form elements of span, or V is linear combination of the vectors 1 comma t square comma t cube. So here we get the values c1a, c2b, c3c, c4d. So therefore we say that S is span of V, and here S satisfies two conditions, linear independent and span of S equal to V. So therefore we say that S is basis for V. Matrix given vectors are linear independent, total vectors are linear independent, then we say that those vectors, linear independent vectors, form basis for the given vector space. So here the given vectors, the vectors are given. So 1 0 minus 3, 3 1 minus 4 minus 2 minus 1 1. So first we check it, these vectors are linear independent or not. So linear independent definitions are, so first det value is not equal 0, then we say that det value of these vectors is not equal 0, then we say that given set of vectors are linear independent. So next one definition is, so the matrix these vectors we write linear combination c1 v1 plus c2 v2 plus c3 v3 equal to 0 bar. In that linear combination all scalar values, using scalar values are zeros, then we say that given vectors are linear independent. That is one method. So one is det method, det value not equal 0, then we say that given vectors are linear independent. Another one is we write a linear combination of the vectors and equate to 0 bar, and we find the scalar values. Those scalar values are zeros, then we say that given vectors are linear independent. So here the next one method is the matrix, the vectors we write in a matrix form or matrix equations form, Ax equal to 0 bar form, or we write matrix A. So matrix A is reduced to echelon form. Echelon form means upper triangular form. In that upper triangular form, number of pivot columns are equal to number of rows of the matrix. Then we say that given vectors form linear independent. Given vectors are called linear independent. So first matrix A is reduced to upper triangular form. So upper triangular form means we make below diagonal elements in the matrix are zeros. So here the matrix 1 3 minus 2 0 1 minus 1 minus 3 minus 4 1. So here we want first row first element 1. By using that one we make below elements are zeros. So third row element minus 3 element value we make 0. So minus 3 plus 3 into R1. So it is the operation. So here in the next matrix, so we apply this operation 1 3 minus 2 0 1 minus 1, and the last row elements are changed 0 5 minus 5 with the operation R3 equal to R3 plus 3R1. Next we want second row second element 1. By using that 1 we make below elements are zeros. The operation is R3 minus 5R2. So here we getting matrix is 1 3 minus 2 0 1 minus 1. So last row values we get 0. Means here diagonal elements are 1 1 0. Diagonal elements are 1 1 0. Means first column second columns are pivot columns. Third column is the free column. So here two pivot columns are there, and in the matrix 3 rows are there. So both are not equal. So we say that given vectors are not linear independent. Here we have one free column means given vectors are linear dependent and they are not form basis for R3. So the matrix has only two pivot columns, first and second columns. So given vectors are linear dependent and these vectors does not form basis for R3. So now the next problem. So vectors are 2 minus 2 1, 1 minus 3 2, minus 7 5 4. So here we apply the matrix A is reduced to upper triangular form. So that form we get 1 0 0 0 1 0 0 0 1. Means here we have three pivot columns. First column, second column, third column are pivot columns. So given three vectors are linear independent and these vectors form basis for R3. So in the problem fifth, so problem fifth, vectors 3 0 minus 6 minus 4 1 7 minus 2 1 5. So determine if v1 v2 v3 is basis of R3. Already we know these three vectors does not form. So first we write matrix form. So that matrix is reduced to upper triangular form. Then we getting the matrix is 3 minus 4 minus 2 0 1 1, last row 0 0 2. So here diagonal values 3 1 2. So these values are pivot columns, pivot positions. So 3 1 2 are pivot positions. So these pivot positions columns are called pivot columns. So first column, second column, third column are pivot columns. So here these three vectors are linear independent, and by invertible theorem, so A inverse exists, means given three vectors form basis for R3. It is the problem solution. So now the next problem. So find a basis for the vector space V spanned by the vectors. So here four vectors are given. In those four vectors, which vectors are linearly independent, and those vectors are form basis for the vector space. So first, so these four vectors we write in linear combination. That linear combination is V equal to 0 bar. So here we write a linear combination R1 W1 plus R2 W2 plus R3 W3 plus R4 W4 equal to 0 bar. So here we write matrix form AX equal to 0 bar form. So matrix A is reduced to upper triangular form by using row operations. So upper triangular form, here we get 1 0 2 0 0 1 1 0 0 0 1. Here the diagonal values 1 1 0 1 1 0. So here the diagonal are pivot columns. Pivot columns are first column, second column, and fourth column. So third column is the linear combination of first and second. So if any one column is linear combination of the any columns, then those column is free column, and given vectors are linear dependent. So now here pivot column vectors are linear independent, and they form basis for the vector space. So here first column, second column, and fourth columns are pivot columns. So these three columns vectors are linear independent, and those vectors form basis for the vector space. Means here W1 W2 W4 vectors form basis for the vector space. So now next problem. So let V1 equal to 0 2 minus 1, V2 equal to 2 2 0, V3 equal to 6 16 minus 5, and H equal to span of V1 V2 V3. So one condition is given, V3 equal to 5 V1 plus 3 V2. Then show that span of V1 V2 V3 equal to span of V1 V2. Also find basis for subspace H. So here in the V1 V2 V3, one equation is given. What is the equation? V3 equal to 5 V1 plus 3 V2. First we write H equal to span of V1 V2 V3, means elements of H are linear combination of the vectors V1 V2 V3. So we write elements of H equal to span of V1 V2 V3 means C1 V1 plus C2 V2 plus 0 V3, or every vector in span. So next we show that here span of 3 vectors equal to span of 3 vectors, 2 vectors, span of 3 vectors equal to span of 2 vectors. We take span of 2 vectors V1 V2. So span of V1 V2 means linear combination of V1 V2, C1 V1 plus C2 V2, that equal to, we write C1 V1 plus C2 V2 plus 0 into V3, 0 into something value, 0 bar, 0 into vector equal to 0 bar. So here any vector in span, any vector in H, it is the form C1 V1 plus C2 V2 plus C3 V3, and here we write V3 equal to 5 V1 plus 3 V2. So then what is the X? In the X we write V3 plus 5 V1 plus 3 V2. So X equal to C1 V1 plus C2 V2 plus C3 into V3 value 5 V1 plus 3 V2. So here we write V1 into V2 into. So here X is linear combination of the vectors V1 and V2. So we will take X is element of span H, and here we show that X is linear combination of V1 V2. So therefore span of V1 V2 V3 equal to span of V1 comma V2 by using the condition V3 equal to 5 V1 plus 3 V2. And here V1 V2 vectors are linear independent, so these vectors form basis for the given vector space. So in the next problem, so let V1 equal to 3 4 minus 2 minus 5, V2 equal to 4 3 2 4, V3 equal to 2 5 minus 6 14. So it can be verified that condition is given 2v1 minus v2 v3. So use this information to find basis for h, that is h equal to span of v1 v2 v3. First we will take linear combination of the vectors v1 v2 v3. So that linear combination satisfies the condition 2v1 minus v2 equal to v3. So v3 place we write 2v1 plus v2 in the linear combination. Then we get linear combination is v1 v2, or from the equation we write the value v1 equal to or v2 equal to or v3 equal to. If we write v1 equal to, then resulting vector is linear combination of remaining two. So one vector is linear combination of remaining two. Then v1 is linear combination of v2 v3. If we take v2 value, then we get given vector is linear combination of v1 v3. Next v3 we will take, then it is linear combination of v1 v2. So in the pair of vectors v1 v2 or v1 v3 or v2 v3 are linear independent vectors and they form basis for h. So now spanning set theorem. So this theorem statement is, let S equal to v1 v2 so on vp be a set in V, and let h equal to span of v1 v2 so on vp. So first condition, if one of the vectors in S, say vk, is linear combination of its remaining vectors, so then the set formed S by removing vk, still span of S. Second condition, h value not equal to z singleton 0 bar, some subset S is basis for h. H value not equal to 0, then S is basis for h. So in the proof, so first, so by rearranging the list of vectors in S, say, so suppose Vp is a linear combination of v1 v2 so on vp minus 1. Then Vp equal to, we write a1 v1 plus so on plus ap minus 1 vp minus 1. Suppose x is element of h, then x is linear combination of the vectors v1 v2 so on vp. So x value we write c1 v1 plus so on plus cp v minus 1 vp minus 1 plus cp vp. So here from the first equation we write vp value in the equation. Then x is the linear combination of the vectors v1 v2 so on vp minus 1. So x is linear combination of the vectors vp so on vp minus 1. So that's the theorem. So here b. So if the original spanning set of set S is linear independent, then it is already a basis for H. So otherwise one of the vector in S depends on the others and can be deleted by part A. So long as there are two or more vectors in the spanning set, we can repeat this process until the spanning set is linear independent. So therefore hence is a basis for H. So if the spanning set is equally reduced to one vector, then that vector will be non-zero. So it is linear independent. So therefore we say that h value not equal to singleton 0 bar. So it is the spanning set theorem. So next definition for basis for null A and column A. So basis for null A definition. The vector x obtained from the equation x equal to 0, 0 bar, then x is called basis for null A. So next the vector x obtained from the equation x equal to b, then x is called basis for column A. So here the vector x obtained from the equation x equal to 0 bar, then x is called basis for null A. The vector x obtained from the equation x equal to b, then x is called basis for column A. So here another one theorem is there. The pivot column of matrix A form A basis for column A. So in the matrix A, pivot columns form basis for column A. Basis for column A. So here the problem is find the basis for column A and null A for the following matrices. Find the basis for column A and null A for the following matrices. So here the matrix 1 0 3 0 1 minus 1 minus 2 1 minus 7 minus 2 4 3. So first if we want the basis for column A or null A. So basis for column A are pivot columns form basis for column A. Free columns or non-zero pivot columns form basis for null A. So first the matrix is reduced to upper triangular form using row operations. So by using row operations, then we get the upper triangular form is so 1 0 minus 3 2 0 1 minus 5 4 0 0 0. So here in the upper triangular form, first second columns are pivot columns. Remaining two columns are linear combination of these two columns, means free columns. So first second columns form basis for the column space. So third fourth columns form basis for the null space. So now basis for the column space are first and second column. First second column first second columns are pivot columns, means first second vectors form basis for the column space. Next third fourth columns are basis for null space. If we want null space vectors, then again we write Ax equal to 0 bar equation. From that equation we find the X matrix. So that matrix elements using vectors are spanning set elements of null A. So we write equations. Here 4 columns are there. So we will take 4 variables. So x1, x2, x3, x4 we say, and this upper triangular form, from the upper triangular matrix we write the equations 1 into x1 plus 0 into x2 minus 3 into x3 plus 2 into x4 equal to 0 bar. Same way second row elements 0x1 plus x2 minus 5x3 plus 4x4 equal to 0. Last row elements are zeros. Here we get two equations. Those equations we write for the values x1 and x2. Those values we write in the x vector. So here we get the vector variables are x3 and x4. We write x3 coefficients and x4 coefficients. So x3 into one vector and x4 into one vector. So these two vectors u comma v vectors are basis for null A. 3 5 1 0 minus 2 minus 4 0 1. So in echelon form of matrix A, first and second columns are pivot. So these columns form basis for column A. So basis for column A vectors are first, second, 1 0 3 0 1 minus 2. So same way next problem. So here same way find the basis for column A and null A for the following matrix. So it is similar to first example. So now next one problem is assume that A is row equivalent to B. Find the basis for column A and null A for the following matrix. So here assume that A is row equivalent to B, that is B is the upper triangular form or echelon form of matrix A. So here direct we find basis for column A. So what is basis for column A definition? So in upper triangular form, pivot columns form basis for column A. So in the upper triangular form matrix B, columns, first column, second columns are pivot columns. Remaining two columns are linear combination of these two columns. So first, second columns vectors form basis for the column A. First column minus 2, 2 minus 3. Second column 4 minus 6, 8. if we want basis for null A, then from B we write Ax equal to 0 form, and we write the equations. Those equations are we write the equations. Here we get those equations are we the matrix B. So 3 rows are there, last row is 0. So here we get 2 equations. Those 2 equations we write for x1 x2 values, and these values we substitute in the x matrix x1 x2 x3 x4. We get x is linear combination of x3 x4. So linear combination vectors span, so it is basis for null A. Minus 6 minus 5 by 2 1 0, minus 5 minus 3 by 2 0 1. So now the second problem is same model problem. So here assume that A has row equivalent to B. Find the basis for column A and null A for the following matrix. So in the matrix B, so pivot columns are first column, third column, last column. So these columns form basis for column A. First, third, fifth columns form basis for column A. So if we want null A, so null A means solve Ax equal to 0 to determine basis for null A. So null A basis elements. So here we get 4 first equation minus 7x5 equals 0. Next equation 3x3 minus 6x4 plus 3x5 equals 0. In that we write x5 equals 0. So here we get the values x1, x3, x5. So remaining values here in the x vector we write these values. Then we get minus 2x2 minus 2x4 x2 2x4 x4 0. Here two variables are there. So x is linear combination of x2 and x4. So these linear combination vectors form basis for null A. Minus 2 1 0 0 0 minus 2 0 2 1 0. So here the next problem is there. Find the basis for the set of vectors in R3 in the plane x minus 3y plus 2z equals 0. So here this equation we write x equal to minus 2y minus z. So in the x vector we write x value, and that values we write linear combination y into and plus z into. So y into minus 2 1 0 plus z into minus 1 0 1. So these two vectors form basis for the null A. So next problem, find the basis for the set of vectors in R2 on the line y equal to 5x. R2 means here we have two vectors x comma y. In the x comma y we write y value 5x. So we get the vector x 5x, x common 1 into 5. So this vector form basis for the null A. So same model problems are there here. So here the problem is find the basis for the space spanned by the given vectors. So here 5 vectors are given. So these vectors in these vectors, so which vectors spanned by the basis set, or in these vectors linear independent vectors form basis for the given set. So first we want the basis for the spanned set means, so we write matrix A. So that matrix is reduced to upper triangular form or row echelon form. In that form, so pivot columns form basis for the given set, and pivot columns are linear independent vectors. So first matrix A is reduced to upper triangular form. So that form we get 1 0 2 2 3 0 1 minus 2 minus 1 minus 1 0 0 16 2 0 0 3. Here which columns are pivot columns? So first column, second column, fourth column, fifth columns are pivot columns. So third column is the linear combination of first second, so it is free column. So here first column, second column, fourth column, fifth column elements form basis for the given set, that is v1, v2, v4, v5. So next problem, so same model, similar model. Find the basis for the space spanned by the given vectors. Here 5 vectors are given. So these 5 vectors are reduced to upper triangular form. So in the upper triangular form, pivot columns form basis for the basis set. So now first the matrix A we write, that matrix A is reduced to upper triangular form. So here we are getting upper triangular form is 1 0 0 minus 1 minus 2 0 1 0 minus 3 0 0 1 0 2 0 0 0. Last row elements are zeros. So first column, second column, third column elements are pivot positions, and these three columns are pivot columns. Fourth, fifth columns are linear combination of these three columns. So these last two columns are called non-pivot or free columns. So therefore first vector, second vector, third vector form basis for the given set, given vector space. So thank you. So namaskar for everybody.